So our next lesson for electricity will be about potential and capacitance. Electric potential difference. Another name for this is voltage. This is actually the external work that is required to bring or carry a charge from one location to another location in an electric field. And we have already discussed electric field in the previous lesson. And so, this voltage will require what we call an electric potential energy. And what is this energy all about? This is actually the energy that is needed to move that charge in that electric field or against that electric field. So the carrying of that particular charge is carried by what we call the electric potential energy, and that is a requirement of an electric potential difference. So when we speak of the word difference, definitely there is a difference in position of the charge from one location to another location, and that is carried by the electric potential energy. And for example, when the electric potential difference, if a volt is raised from 1 degree to another, like 1 volt difference, this will actually provide the electron a value of what we call an electron volt energy. So that is just raising a specific amount of difference, which is equivalent only to 1 volt, and that is already a value of an electron volt energy. And what is this equal to? This is equal to 1.602 times 10 to the minus 12 erg if the unit is in erg, but there is another unit in joules, and that will be equivalent to 1.602 times 10 to the minus 19 joules. And when we speak about absolute electric potential, what is this with respect to the electric potential difference? So what is the difference between the two? Actually, when we speak of the absolute, that is the entirety of the absolute electric potential, wherein electric potential difference is just simply a component or a parcel of the absolute electric potential, which is actually the amount of work, the same as electric potential difference, which is the amount of work to be done to bring an object to its current location or current position from a specific point from that infinity. So meaning to say, we do not know where it comes from as long as it is infinity. So basically, that is the absolute value, wherein a specific value is caused only by the electric potential difference. So in here, we are using analogy, or we will be using analogy to understand what is the meaning of potential difference, and then also the energy that is required for bringing a charge from a specific location to another location or another position in a particular electric field. So in here, analogy of electrical potential to a gravity. So our planet Earth has a gravity because it has a mass, and for example, it will be attracting a specific type of object, so it will be called an attraction or gravitational attraction between the Earth's gravity and the object. So supposing that our Earth or Earth's gravity this time will be the electric field, and so the charge here will be the apple, or the apple will be the charge. Now we are raising that apple from the ground, maybe, or moving on to another position. So by the use of our hand, and that hand will now be the one that will lift the apple from the ground to a higher position. So the hand will be also analogous to the electric potential energy. So that is the energy that will carry that charge from that particular electric field. And so the difference between the position, the original position, and the new position will be the distance traveled by that apple, which is also analogous to our electrical potential difference. And that height is now called voltage. So we are now going to look at the formula for potential difference, and that is given by the symbol V is equal to W over Q. And V in here is the potential difference given by the unit voltage, while Q is the charge given by the unit coulomb, and work, or W, is work done given by the unit joules. So in the case of parallel plates, the two parallel plates will develop an electrical field. So a potential difference can also be calculated from that two parallel plates with a distance called letter D. And the formula given is equal to V is equal to E times D, wherein V is the potential difference and E is the electrical field, while D is the distance between parallel plates. We are now going to utilize the two formulas for a potential difference and also to calculate potential difference within a parallel plate that has an electrical field within the inscription of the parallel plates. And so we have our first problem, a potential difference between a metal plate. So there is a metal plate that is already having a potential difference of 40 volts. The question is, which plate is at the higher potential? And B, how much work must be done to carry a positive 3.0 coulomb of charge from B to A and from A to B? So there is a question between either B to A or A to B, because you see that in question the question for letter A is there is a confusion first as to which plate is having the higher potential, meaning where will the charge of 3.0 coulomb be directed to, either from B to A or A to B. Now, as we will be answering that later, let us see how do we know that the electric field, so an electric field also has a direction indicated, is correct. So we will check that out also as we see, or we will be looking into the sketch of this problem. And for letter D, if the plate separation is 5.0 millimeters, what will be the magnitude of our electrical field? So you see that in letter C we are going to answer whether the indication of our electrical field, which I presume that in the illustration there is already a direction for our electrical field, and at the same time there is a separation of that plate of a value of 5 millimeters in a specific magnitude of electrical field. So we will look at now the sketch. So this is the sketch. Okay, now there is the direction indicated already of our electrical field. We will try to check letter C later if the electrical field direction is indicated is correct or not. And so this is plate A, and plate A is actually positively charged while plate B is negatively charged, and there is the distance between them. As it was discussed in our previous lesson before this one, we are already talking that when there are different charges, it will really produce an electrical field, and so therefore between A and B there should be an electrical field within. So our particular charge will be moved from A to B or B to A within the electrical field, and so the moving of that charge will be utilizing an energy, and when we are able to create the movement, we will be producing potential difference. And so, for example, if this is the test charge with a value of positive 3.0, so we will now be trying to answer letter A later on. So that will be our test charge. So we are going to answer letter A. Which of the two plates will have the highest potential? So for example, we have plates A and plates B, and if there is a charge somewhere in here, so plates A in here, plates A will actually produce the repulsion, supposing that a test charge is positive, while plate B will produce the attraction or the attractive force. So again, the our what do you call that is E value. The E value, which is directed from A to B, is our field or electrical field that was generated, is moving towards B. But in that case, when the positive test charge will be brought near to A, it will be repelled, so naturally it will be moved towards B, while B is also attracting it. So definitely this is the lowest position of our charge. So when we are going to add an energy and move it towards A, so that is where the energy is required to move the charge, because that is actually the one that requires energy, because this one, this positive charge, as it is naturally attracted to B and naturally repelled by A, will definitely be located in here. But when you are going to apply an energy, then you will be moving the potential difference from B to A. So definitely the answer is, where do you find the highest potential difference? And that will be somewhere in A. So A is where the higher potential difference can be found. So to calculate for the work that is done by moving of the test charge from B to A. So in the case of the default, the work done in transporting the charge from point A to point B, but in this case it's from point B to point A. So it's given by the formula W, or the work, which is equal to the charge multiplied by the final position, which is supposed to be in the B, minus the initial position, which is in the A. So that's why it's voltage. So voltage simply means the position or the potential difference, which is supposed to be in B minus A, is given by, also described by, Q times B. And so the magnitude of the work done in carrying the charge Q, which is this one, through a potential difference, the difference is in the case of B to A, is given by the formula Q times V. Thus, the magnitude of the work done in the our presentation or in our current situation is given by the formula W, which is again positive 3.0 coulomb of charge times a voltage. According to the problem, it already has a potential difference of 40 volts. Therefore, that will resolve to 120 joules. But we would like to get the kilojoule value, so divide that by 1000 and you will get a value of 0.12 kilojoules. So going back to our problem, and remember that a positive charge between plates is A and the charge is a repulsive force. So positive work, which is 120 joules or 0.12 kilojoules, must be done to drag the charge from B to A. So to restrain the charge as it moves from A to B. So in order to create a negative effect supposed to be from A to B, we are actually moving the charge from B to A. So there is actually a negative work that is done in here. Alright, so that is why the proper way is actually negative 120 joule is done. So the work is done into the system, not the system is doing work going out. So work is actually applied within the system. So that is why we will write the value of negative 120 joules or negative 0.12 kilojoules. Now for our next problem, letter C, a positive test charge between the plate experiences a force directed from A to B. So the question is the direction of our electrical field correct? Well, according to the definition, that electrical field lines should be radiating outward from positive to negative. So if this is the direction of our electrical field as it was indicated in the illustration, then therefore according to the definition, this electrical field is actually correct. And for letter B, for letter D, for parallel plates, we can actually calculate the voltage generated by a parallel plate if there is a value for our electric field, and the dimension or the distance, that is the thickness of the distance between plate A and plate B. So since our voltage is already defined and the distance is also defined, but we do not have the electrical field, so therefore we can play with the formula and we derive the formula for electrical field as equal to the voltage divided by the distance of the two parallel plates. Therefore our voltage will be 40 volts divided by 0.0050 meters, because everything should be in volts and meter. So therefore our value for our electrical field is 8.0 kilovolt over meter. Now this is now our value for electrical field, but in our previous lesson electrical field should be in Newton per coulomb, but volt per meter is just simply also equal to Newton per coulomb. So therefore this unit is also referring to the electrical field for the SI or Standard International Unit for our electrical field. Formula for absolute electrical potential, that is given by V is equal to K times Q over R. And for our potential, which is V, should be equal to the K constant, and that is 9 times 10 raised to the power of 9 newtons times meter square over coulomb square, while the R is the distance from the charge in terms of meters, and Q here is the charge in terms of coulomb. We will now apply the formula that was presented earlier in our problem today, and that would be about a thin nucleus. So, well, when we speak of nucleus, that comprises the particles of proton and neutron particles. And remember that protons is the one that carries a charge, which is a positive charge, while neutron doesn't have any charge at all. So in the problem here, a thin nucleus has a charge of 50 times those elementary particles, which is the charge of one proton. And since there are 50 protons in there, so that's why we have the positive 50 times E. The question is, find the absolute potential V, which is the value for the absolute potential V at a radius of 1 times 10 to the minus 12 meters from the nucleus. Okay, so we will be able to find for the value of V. Alright, so we will be making use of the formula, and remember that our radius is 1 times 10 to the negative 12 meters from the nucleus, so that is quite very small. And for letter B, if for example a proton is already released from this point, from the nucleus, how fast will it be moving when it is 1 meter from the nucleus? So it's moved away from the nucleus, brought to a 1 meter distance. Okay, so we will be able to solve for that one later. And first we will have to check out the nucleus or the atom of a tin, and this is the atom of a tin, so we will not be able to see the individual protons and neutrons in this illustration, but the one at the center with the symbol SN is where the protons and neutrons, or generally called the nucleus, can be found. Okay, so for our first problem, letter A, find the potential value, which is V, if the radius is 1 times 10 to the minus 12 meters. So our formula, which is V, is equal to the K constant times Q over R. Our K constant is always the same, 9 times 10 raised to the power of 9 newtons times meter square over coulomb square. And our Q, which is the 50 of those positively charged protons multiplied by the charge of each proton, which is 1.6 times 10 to the minus 19 coulomb. This is the quantity or the value for our elementary particle, the charge of our elementary particle, and multiply that by 50 divided by the radius, which is 1 times 10 to the minus 12 meter, or 10 to the minus 12 meter. The value will now be equal to 72 kilovolts. So that is the amount or the value for the absolute potential V if it is placed about a radius of 1 times 10 to the minus 12 from the nucleus. So they are very close to each other because the radius is very small. Now for our letter B. Okay, for our letter B, if a proton is released from this point, how fast will it be moving when it is 1 meter from the nucleus? Alright, so for letter B, the proton is released by the nucleus and it flies out to infinity. You know, when the word infinity is quite very difficult to understand because it has no boundary. So it can actually go on, continue, and moving on into infinity. So the absolute potential at a point is the potential difference between the point in question and the infinity. So this is what we are going to solve. What will be the absolute potential from that point to infinity? And so we will be solving that out later. But we have to remember that earlier when when we are just simply solving for the proton within the nucleus, we are able to generate 72 kilovolt of those protons. But since from there, that is where our proton will be moving from that nucleus to the infinity. And so we would simply assume that our infinity is at 1 meter. When we speak of 1 meter, this is only an assumption. Nobody knows the meaning of, or nobody knows where infinity will stop. Okay, so it's just to assume that we will indicate a 1 meter value for our infinity from the nucleus to consider it to be an infinity. So let us compute for V when our R, the distance from the nucleus, is at 1 meter. That is an assumption for our infinity. And so the formula is still the same. Our absolute potential value, which is V at 1 meter, is equal to K times Q over R. And K is the same, it's constant, 9 times 10 to the power of 9 Newton times meter square over coulomb square. And our Q is also the same, 50 of those elementary particle, which is 1.6 times 10 to the minus 19 coulomb, divided by the assumption, which is 1 meter as our infinity value. So that will give us a value of 7.2 times 10 to the minus 8 volt. So therefore, this is actually very small compared to the earlier calculation, which is 72 kilovolts. So according to the description here, this is essentially zero in comparison with the 72 kilovolt. So as the proton falls through 72 kilovolt, we will now be answering how fast will it be moving. So the only way to do that is to look at the relationship between the kinetic energy that is related to potential energy, and this is the conservation of energy. So here is if kinetic energy is gained, then we will be losing some potential energy, or vice versa. When we are gaining potential energy, then we will also be losing some kinetic energy. So in the original calculation for our potential energy, that is equal to the mass times gravity times the height of our potential energy position. But we are talking here about electrical potential energy, so that is equal to Q times V. But our kinetic energy can always be the same, which is 1/2 mv square of the final minus 1/2 mv square of the initial position. And so since according to the structure of our question, if a proton is released from this point, definitely originally the proton is at rest because it was just released at the position where the velocity is equal to 0. So we can convert that into 0 later on. And so to calculate it, our Q times V is always the same, 1.6 times 10 to the minus 19 coulomb for the elementary particle, because we're talking about a proton here, multiplied by the voltage which is experienced by that particle when it is at the nucleus. So that is having a value of 72,000 volts or 72 kilovolts. That will be equal to 1/2 mass This 1.67 is actually the standard value for our mass for our proton times 10 to the minus 27 kilogram multiplied by the square of its velocity. So if you wish, I will have to show the cancellation first. Okay, if you wish to solve for the final velocity, you will have to transpose all this value and provide a value for the square root of the final answer, and our final V will be equal to 3.7 times 10 raised to the power of 6 meters per second. So that is extremely very fast.